Okay, so we have a very funny anecdote. We have a very Commonwealth-themed CAPS today. Our next speaker is Ben Boyd, all the way from University of Cambridge. He's doing his PhD there with Professor Casey Mandel, and he's visiting Professor Gautam Narayan here and myself as well. Ben works, so Ben is doing his PhD there. Prior to that, he was doing his master's at Imperial College on machine learning. He does a lot of cool stuff with ML, AI stuffs, and Supernova, and other stuffs as well. Thank you, Ben, and please take
Thanks,
it.
Aya. Hi, everyone. I'm Ben, and today I'm going to talk to you about hierarchical Bayesian modeling for white dwarf calibration and supernova cosmology. This work has been in collaboration with various people from UIUC, including Gotham, Ayan, Aidan, and Mai. So it's really nice to be here in person and see everyone. So yeah, let's just get into it. So what do I mean by a hierarchical Bayesian model? So here you've got Bayes law, Bayes rule, where you're saying your posterior, which is the probability of your parameter given your data set, is proportional to your likelihood times your prior. And when I say hierarchical, I'm just saying that the probability of your data set given parameter is equal to the product of the likelihood of each data point. So that is the probability of each data point given parameter. So you can do quite powerful things with this. A good way to kind of visualize the hierarchy is using a graphical model. So here, you can infer object-level parameters, such as the y parameter, given data 1 and data 2 from an individual object, whilst simultaneously dealing with like a nuisance parameter, gamma 1 or gamma 2. But then you can make some powerful inferences on the overall population. So that will be the z parameter here. And depending on your application, z could be different things. For example, it could be a systematic that's influencing the whole of your data set, or it could be something like cosmology. So I'm going to give two kind of case studies of different hierarchical models that I'm using in my research to give you an idea of what you can do with these types of analysis. So the first problem is DA white dwarf spectrophotometric calibration. So we'll soon be, or maybe we're already even there, in the regime where our systematic uncertainties are dominating over our statistical uncertainties. And this is only going to get worse as we get more data. The statistical uncertainties will shrink, and we'll need to be very careful with the systematics. An example of this is that in supernova cosmology, there's a strong degeneracy between your predicted redshift but also the calibration of your relative color of each supernova. And this type of signal is the same strength of something that could cause something like a W tension. As you can see here, you've got the DESI results where it's hinting at a non-lambda CDM cosmology. I'm not saying that this is caused by color calibration, but I'm saying if we're making kind of these sort of statements at this level of precise cosmology, we need to be very careful with our color calibration. So we're now in the regime where this sort of thing is really important. So this basically motivates the need for a set of faint standards that are across the whole sky that you can use to calibrate the next generation of surveys. And I'm saying faint because our surveys are now getting deeper and deeper into the sky. So we need something that's faint so it's not saturating our camera straight away. So this is what's motivated the all-sky network of 35 DA white dwarfs that we've got as a collaboration. Of those 35, 32 of them are very faint white dwarfs that are useful for these types of applications. But 3 of them are bright DA white dwarfs that are already in what we call the CALSPEC system. So these are a set of standards that are already calibrating our surveys. So it's kind of, you can put them on the same scale if you like. So for the 35 white dwarfs, we have data. We've got 6 Hubble Space Telescope, bands from the UV to the near infrared for all of them. We've got ground-based optical spectra for all of them again. And for about half of them, we've got some space-based STIS UV data. So you need to take all of this data and carefully model each of these DA white dwarfs so that they can be used as standards. So in previous work, we've already achieved sub-percent accuracy using this network, just using the optical data, the optical spectroscopic data. So this was in Axelrod 2023 and Gotham's paper in 2019. But we still feel like we could do a little bit more. And we believe that we can achieve a high level of accuracy by modeling everything hierarchically. The reason for this is you get improved constraints on instrumental systematics that affect the whole network. This is, again, this population analysis that I'm referring to. And you get a fully Bayesian treatment of your uncertainties from your data right through to your parameter estimates. It's never been done end-to-end for the whole network before. So that's what we're going to try and do. So here's the graphical model of the hierarchical model that we've designed. As you can see, there's a lot going on here. I've called it DA model, or you can call it DA model if you like. But I'm just trying to illustrate here, it's hierarchical in multiple ways. There's 35 white dwarfs. As I said, there's coverage in the 6 bands. There's multiple observations per object per band. There's HST cycles, so some of the sensitivity of some of the CCT, of the CCD, sorry, the photometry, it changes over time, so you need to take the actual time of the observation into account. And like I said, we've got multiple spectra at different wavelengths for some of the objects, so it's very hierarchical. So there's a lot going on here, so it's easier to kind of just look at the forward model. And what we do is we begin with a template, and this template is a theoretical template that describes what a DA white dwarf should look like. So it's a black body spectrum with these hydrogen absorption features. These are the Balmer series, and this is what makes DA white dwarfs so special. They've got pure hydrogen atmospheres, so they kind of give you this very clean SED. And it's the effective temperature and log surface gravity that affects the strength of these absorption features. So what you're able to do is basically have a function that is a function of wavelength, log G, and effective temperature that you interpolate to kind of give you an underlying SED. So after we use that, we can then build on it. And the next thing to build in our model is dust, because there is a lot of dust in between us and everything else in space that you need to consider. So you can apply your dust law. So we've been using quite an old dust law, Fitzpatrick 99 dust law. We can actually switch this out with other dust laws, and we're in the process of doing it. I chose this one because previous works used this, so it's easier to kind of compare results. But the idea is that the dust law is parameterized by AV and RV. AV is the extinction, and RV is the ratio of extinction to color excess in the B minus V color. So what you're doing essentially is making this SED a dusty SED that is also a function of AV and RV as well as the other parameters that I said. After you've done that, you've got your dusty SED. So here's my dusty SED. And you add a distance-like parameter. It's not exactly distance because we don't have radial information of the white dwarfs, but essentially this parameter makes the SED dimmer at all wavelengths. And this is something you also need to infer. And you then convolve that with your bandpass filters, and you should get some synthetic photometry for the 6 bands that I was talking about. Other kind of details that we're modeling are these instrumental systematics of Hubble. So you've got the 0 points in each band. You've got the change in 0 point, so that sensitivity changes over time. You've got a count rate non-linearity, particularly in the near infrared, so there's not a linear relationship exactly between like the counts and the flux that you get. So you need to model that, which is a bit tricky. And then there's also a dispersion in each band, and we're modeling the photometry using student T distributions rather than normal distributions because you've got fatter tails to kind of deal with what you would call outliers. So for that, you need to infer a degree of freedom parameter. So that's how you do the photometry. To do the spectra, you take that just the SED from before, apply some normalization. It's an arbitrary normalization that you infer as well, but it's more of a nuisance parameter. And you convolve it with a normal distribution. And what this is doing is smoothing the features of the absorption features. And the reason for this is the resolution of your spectrum is never going to match the resolution of your theoretical SED. So after you've done that smoothing, you should get something that looks like this orange line. As you can see, there's still a difference between this orange line and the observed spectrum. And this is what you can think of as like a wavelength-dependent systematic. And this is, again, an instrumental effect, or it could be something like the atmosphere. But it's a nuisance function that you need to infer. And that is done, it's been done previously using a Gaussian process in Gotham's work. But what we found is that these kind of systematics are very smooth, and Gaussian processes are quite expensive, so we could actually get away with using something a bit cheaper. So in my version of the model, we use a cubic spline, and you get the same kind of results, but you benefit from some computational speedups where you can model the spectrum as the product of normal distributions evaluated at each pixel. So it's doing that IID thing again, and you can make things a lot quicker, which is great because it allows us to do this hierarchical analysis. So it's the exact same method for the UV STIS data. All you're doing is evaluating your model at a different set of wavelengths. So it's the same there. So let's skip over to the results. We get very decent results. We get the best results yet on this network, where on average we've got an RMS of 4 millimag from the UV to the near infrared. As you can see, we're getting about between 3 and 4 millimag from the UV to the optical, but then things get a bit worse in the near infrared. We're getting about 8 millimag RMS, but that's to be expected because it's quite noisy data, and we're also trying to deal with that count rate non-linearity that I was referring to earlier. Some more in-depth comparisons to old pieces of work. We're doing better in all the bands than the previous Axelrod 2023 paper. You can see here that the addition of the STIS UV data isn't improving things too much. In fact, in some cases, it's actually making things worse. But that doesn't mean to say that we should just throw away that data that people spend a lot of time doing proposals for. We should actually think about how our model could be adapted to kind of cater for this data. So you might need to rethink the theoretical UV modeling of the white dwarfs, or you could try different dust laws. Like I say, I'm using a 25-year-old dust law that I could probably swap out with a more recent one. So I'm in the process of doing that with the Gordon 2023 dust law. You can also see how the UV data is kind of affecting the average SED. You can see we're getting like a 7% change here just by adding that data, but then predictably the other wavelengths are staying the same because you're not adding more information there. You can look at the systematics. We're getting like this, like I say, non-zero change in 0 point across Hubble cycles, which is interesting. And we're also able to kind of infer this count rate non-linearity. So it's actually quite strong, this -2 millimag per mag. Yeah, it's definitely non-zero, and it's consistent with what the literature has shown, which is cool because we've used a different approach here. So the SEDs that we get, here's what the SEDs look like that we've managed to model. You can then convolve them with bandpass filters from whatever survey you like in order to do cross-calibration. So I get a prediction of what my synthetic magnitude should be for this survey, and then I can plot the residuals between that and the observed data. So that relies on the fact that these objects have been observed in the survey that you're looking at, but because it's an all-sky sample, the chances are you will have got some of them. So here are the residuals for the dark energy survey. As you can see, we're getting decent residuals, like between 5 and 7 in GRI, and then things predictably tail off in the near infrared. So this is really cool because it's a completely independent data set that we're getting some decent consistency with. And what you can do using this sort of kind of method is you can use RSEDs for cross-calibration between surveys. So we're already in the middle. Well, we've got collaborators that are using our SEDs to combine supernovae catalogs to kind of put them all on the same axes. So yeah, we're really excited about that. Future applications, so it's a hierarchical model. So of course you can make some inferences on the population. So like the dust population, for example, what distribution does this RV follow? These results, this is what we get, but the results shouldn't be taken too seriously because we've got quite a heavy selection effect in here, but it's more of a demonstration that the framework is able to make these sort of predictions. Another thing is that it's really scalable now, mostly because of that cubic spline thing. It used to take over a day per object on a CPU, so that's 35 CPU days, and now we're doing it in about half an hour for the whole sample simultaneously on a GPU. So yeah, this combination of great speed-ups plus this population analysis, you could really apply this to a different set of white dwarfs and get some really meaningful population statistics, like such as the DA white dwarfs in Gaia. There's a lot more of them, so you could get some interesting statistics. And then the final thing to say about this work is that we're getting very decent RMS residuals in every kind of wavelength regime that we have spectroscopic coverage for, but we are missing some spectroscopic coverage for this near-infrared. It's always hard to do the near-infrared because it's more noisy, but we do really think if we had a bit more data, we'd be able to reduce this RMS to make them better standards in the NIR. So something like some near-spec data would be fantastic from JWST. And it's completely trivial to add this to the model. It's just evaluating it at a different wavelength range. So yeah, we'll be ready for that if and when it comes. Okay, that was the first case study, and I'll quickly now do the second case study. So the second case study is selection effects in supernova cosmology. Our surveys have a bias to detecting supernovae with certain characteristics. For example, you're definitely more likely to detect a bright supernovae than a dim one, probably a longer lasting one because it hangs around for longer, or a bluer supernova, for instance, depending on the filters that you've got. And if you don't account for this selection effect, then you're going to get a bias in your cosmological analysis if you just naively just assume that this is the data set. So you need to account for it, and that's what this work is doing. So a quick look at how we analyze supernovae. A common way to do it is to kind of look at the B-band and V-band light curve, for instance. This is for an individual supernova. And you say that the peak apparent magnitude in B-band is equal to the distance modulus, which itself is a function of redshift condition on cosmology, plus a 0-point absolute magnitude. And then you've got some kind of correction terms here where we notice that longer-lasting supernovae are brighter, which is captured by this alpha term, and the bluer supernovae we find are also brighter, which is captured by the beta term. So our observables are the kind of colored symbols here, and when we're doing our hierarchical analysis, we're inferring these relationships as well as the cosmology. Yeah. And if you plot the supernovae on the Hubble diagram, it's literally the shape of this arc is what's giving you constraints on cosmology. So that would be all well and good if we actually did observe all these supernovae, but we don't. We actually observe them up to some limiting magnitude because our telescopes have limits in what brightness they can detect. And if you kind of naively fit this line, then it's going to be a bit lower than the red one, and that will give you this kind of black posterior here, which is way off the true cosmology. So the question is, how do we deal with this effect when we literally only have access to this yellow data? So one method that is common in the field is what we call bias corrections with simulations. The idea is that you split your real data up into redshift bins, and you then switch to simulations. So these are SNe state-of-the-art simulations. So these are survey simulations that are in the simulation, like scanning the sky and saying, like, this is the survey plan, this supernova was detected, this one wasn't. And you're able, because it's a simulation, to work out how far on average is your distance going to be off from the truth, because you have the truth because it's a simulation. And then once you have that average in each bin, you switch over to the real data on the Hubble diagram and push it up by that amount, and then you can refit your cosmology, and it should hopefully be equal to the true cosmology. Other things about this method, you can do it in higher order bins in terms of color and stretch. We really like it because so much effort has been put into these simulations. They even have complex factors like the weather to kind of consider, but we're not too sure about it because it's all we have, but we don't have this unphysical binning, and we'd rather kind of not assume this fiducial cosmology to then predict cosmology. Another approach is a hierarchical Bayesian model. This is the thing that I've been talking about a lot, but a lot of the time we're limited to only being able to select an analytical selection function, which is a simplification of the problem. You can say that's a step function where there's no probability of detecting a supernova that's dimmer than a certain magnitude. Or you can say it's kind of this kind of smoother Gaussian CDF where you're effectively upweighting the probability of detecting a bright supernova and downweighting the probability of detecting a dim one. So we like this because you can use it in a hierarchical Bayesian model, but it is a big simplification on the selection effect, which we'd like to avoid. So is there a way to combine the best of both? We believe you can, and we believe the solution is to use something called simulation-based inference. If you've not seen simulation-based inference before, of course, it involves a simulator. In this case, this would be like our survey simulator, where you input your cosmology and your output, so your supernova observables. And the neural network is learning a probabilistic relationship between the two, and it's up to you which probability distribution you'd like to learn. So which probability distribution do we want to learn? We could do these, the posterior or the likelihood of the whole data set at once, but the problem is these are quite high dimensional and kind of difficult to train. And as well, I'd need a different neural network for every cosmology that I was trying to constrain, which is not ideal. We instead proposed, shock, that we split it up into a hierarchical Bayesian model, and we say that the likelihood of the whole supernova sample is equal to the product of the likelihood of each supernova individually. And the benefit of doing this is that you are learning something there that is lower in dimension. It's only 3 dimensions because it's these 3 observables. And there's a clever way that you can kind of train it independent of cosmology. You're only learning here the selection effect that is specific to your survey, not to the cosmological model that you're trying to constrain. So for that reason, you can reuse this one neural network. Yeah, and it's still pretty quick. You can use it with Hamiltonian Monte Carlo sampling. So to learn the probability distribution, we use a normalizing flow. And a normalizing flow is essentially converting a simple Gaussian distribution after a series of transforms into your complex distribution that you're trying to model. So for us, the likelihood. And the transforms are what the neural network learns, and you also there feed in your conditional information. So this is the sort of architecture that we're using to learn the distribution. So a quick test to prove that this works, we're doing it on a toy model to kind of check that it works. So the toy model is actually assuming an analytical selection function. We do this because we've got an analytical solution to this, so we can really check that the normalizing flow is learning what it should, and then you can place it in your hierarchical model and compare the analytical posteriors. So this is what we do. This is what we should be learning. This is the analytical solution where, as you go dimmer, you've got this push of the likelihood towards brighter magnitudes. And in blue, we have what the normalizing flow learns. It's doing a pretty good job of noticing this difference, but it's also 3D, so you need to be seeing the same match in all 3 dimensions, which we do. And when you're satisfied that your normalizing flow has learned as much as it can, you can then give it to a hierarchical Bayesian model to then constrain different cosmologies. So you're reusing that same normalizing flow in different HBMs. So here you can see that it's doing a pretty good job of constraining a WCDM cosmology, and here it does a good job of constraining a lambda CDM cosmology. So with other techniques, you would need different neural networks for these 2 problems, but we're using the same one to constrain both of these. And we could constrain whatever cosmology you like, as long as you kind of give us the distance relationship as a function of redshift. Another thing is that this work is pretty scalable. The examples that I showed you were using 2,000 supernovae, but we wanted to see what would happen if we used a bigger sample, like 50,000 supernovae. And it still deals quite well. As you can see here, we're getting pretty decent agreement again between the analytical and the normalizing flow posteriors. The reason that it scales well, because HBMs don't normally scale that well, is because we can marginalize out latent parameters. So the number of parameters that we're inferring is not getting bigger with the number of data points that we have. So that's a little trick that you can do to allow it to scale. Yeah, and it takes under an hour on a GPU, which isn't so bad for your cosmology constraints that you've been waiting years for. So yeah, we're very pleased with this. But naturally, the next thing to do is, okay, can we learn something that we don't have the analytical solution for? We don't have the pen and paper solution for this complicated likelihood that uses these state-of-the-art survey simulations like SNe Ia. So what we're in the middle of now is training our normalizing flow on these state-of-the-art simulations. So I'm working with Ian, who's helping me get some SNe Ia sims for LSST, and this is the kind of relationship that we're trying to learn. So after we've learned this with the normalizing flow, we can then apply it to real data that's come from that survey. So say we train it on DES, we can try it on the DES data and get some real constraints on real data. So yeah, we're pretty excited about that. So yeah, I'll just leave you with my summary slide, kind of summarizing the two case studies that I've gone over today. And yeah, I'll thank you for listening. Yes.
Let's see. So for the first part, does this rely on the SEDs being absolutely correct?
No,
Okay.
I'm inferring that calibration. So yeah, it's not absolute calibration. I guess you could call it relative calibration, but it's up to you where you put that 0 point. So you could put it. Sorry, there's quite a lot of slides to go back here. You could determine this 0 point by the 3 brighter CALSPEC standards, so then it'd be consistent with the CALSPEC system. Or you can just arbitrarily set the 0 point wherever you want. But I'd say that this is relative calibration rather than absolute calibration. But that is what is important for a lot of cosmology. Like color is a relative measurement. So yeah, to motivate cosmology, this relative kind of calibration is enough. But yeah, there's a lot of effort going into absolute calibration. I was at a conference last week, and it's pretty tricky. Yeah.
But does the tilt have to be right in the models?
Say again.
Does the color have to be right in the models?
Does the color have to be correct?
I mean, I can move that line up and down, and that's a 0 point. But I could also tilt it.
Yeah, so we're in control of the tilt.
Okay.
That's, yeah. We just don't have control. Well, we do, but we have to manually set the overall calibration. But as comparing one wavelength to another, that is what the model is trying to infer. And that's determined by fitting these SEDs.
Yeah, I'm just trying to figure out what if these SEDs were total fantasy and had nothing to do with the object? Like, how would we know?
Well, it's a good point. It depends what you want to do with our model. If you want to make some kind of physics claims with our astrophysical claims, then yeah, it does matter that the model is made up. But if you're just trying to use it as a calibrator, then we just want the model to agree with the data.
Okay.
And then after we've kind of all agreed on that, then you have an SED. So it really does depend on the use case of what you're trying to use this for. But yeah, there is plenty of flexibility in the model. For example, like the SED doesn't have to be the exact same slope as my observed spectrum. The spline and the dust law are allowing for like additional flexibility to that. Yeah. But yeah, really, we just want to get really good agreement between the data. For calibration purposes, we just need something that we can model very well. And yeah, but if you want to do astrophysical stuff with it, yeah, of course it matters that your SED is meaningful.
Okay.
Yeah.
Yeah.
Can you please once again explain those two rows shown in red? Are those your
So,
numbers?
Yeah, okay. So this kind of delta Z 2022 is comparing how the 0 point has changed from cycle 20. So between cycle 20 and 2022, the 0 point of each band has changed by that much. And
So-
between 20 and 25 is changed by the row underneath it. So this is, yeah, this is, yeah, well known with the Hubble data.
So what really caught my eyes, I wanted to ask, is that normal that there's a plus minus 1.003 of error bar on the first column, second row?
First column, second row.
Second row
So,
within the red.
that is because we didn't have data for that one, so that is just the prior.
Okay.
Yeah. So yeah, we didn't actually have data in cycle 25 for that one. So yeah, we can't comment on that one. Yeah, should make that clearer. Yeah, and then the other parameters, you've got kind of your dispersion in each band, so how much are you expecting things to vary, because it's not going to give you perfect estimates every time. You've got your degree of freedom, so which is, yeah, parameterizing the student t distribution, and that high degree of freedom here is telling me that I might actually get away with a normal distribution. Yeah.